Hello class, I'm going to do a very quick demonstration on how to prove Einthoven's law. Einthoven's law states that lead 1 plus lead 3 should equal lead 2. In this demonstration, I'm going to show you how we measure the upstroke of the R and the downstroke of the S if it's there. Then how to take the algebraic sum of those two measurements. Then after I show you Einthoven's rule, I'm going to show you how we map on the compass the person's mean electrical axis. And the mean electrical axis is the average sum, the average vector that best represents the direction that the current is moving during ventricular depolarization. So let's get started on our measurements. The first thing you need to do is get your EKG tracing and find lead 1. Find your R. For most of you, this should be an upward or positive deflection. Take your ruler and do your best to connect the PR segment to the ST segment and draw a line connecting them. It's not rocket science, so make your best fit line. The next thing you do from that line, measure the upward deflection for your R and mark that over here in the column. So this is a +8 for an upward deflection. You can either count the lines in the boxes. Each box is a 5 by 5 millimeter box. Or perhaps now is a good time to actually remind yourself how to measure in millimeters using a ruler. So again, that's 8 millimeters in an upward deflection. There is no S or downward deflection in this tracing. So I'm going to put a 0 for the S. Now I'm going to take the algebraic sum. Overall, that is a +8. If, let's say, you had a negative deflection for your S, and it was a -1, let's say, then in that example for you, let's say you had a +8 and a -1, let's say that's what you got, then you would take the algebraic sum of that. A +8 plus a -1 would give us +7. Again, your own personal EKG, you might not have a negative deflection for the S. And if you don't, like I did in mine, it's just 0. Let's do the same for lead 2. Again, I'm going to try very hard to make my best fit line going across the QRS complex. I'm going to measure the upward deflection. Again, in this one, there is no downward deflection. And in millimeters, this comes out to be a +6. The algebraic sum is again +6. Now, moving on to lead 3, this is my R. It's going inverted, downward stroke, negative deflection. Those are all the same kinds of terminology that you can expect to read. I'm going to measure that downward R from my baseline, and that gives me a -2. Again, there's no S coming above that baseline draw, so I'm going to put a 0, and I get a -2. Now let's prove Einthoven's law. Einthoven's law says lead 1 plus lead 3 equals lead 2. A positive 8 plus a negative 2 is a positive 6. So my tracing proved Einthoven's law. It doesn't get much better than that. If you came close to about 1 to 2 millimeters, then I would consider that successful. Maybe you have a lot of background noise, or maybe it was difficult to get your measurements. Now moving on, how do we calculate, using those measurements, a person's MEA using the compass? Well, just to remind you, down here, this represents lead 1. It's negative on the person's right wrist and positive on their left wrist. This picture should represent your patient's heart looking up at you. So it's their right and it's their left. In class, you were told that the normal values for an MEA are from minus 20 right here all the way over to plus 100. So all of this is considered normal. In your lab manual, you're told that from minus 20 to minus 30 is a left axial shift, and then anything above minus 30 is a left axial deviation. For the right side, anything from 100 to 110 is a right axial shift, and then anything beyond 110 is a right axial deviation. Many students ask, well, what's this whole area up here? What would this be? And that's no man's land. No one should have an MEA up in that area. That would be pointing up and to the right. That would suggest that the ventricles are depolarizing from the apex up towards the base, which is completely backwards. If you calculate an MEA that ends up here, you've either calculated it incorrectly or you have strapped on the leads backwards, and you should go check them. Okay, so how do I plot these values that I calculated here onto the compass? Well, I only need to use lead 1 and lead 3 for this. So lead 1 is a plus 8. So notice down here for lead 1, they are showing you guidelines that are going vertically. And here is 0 for lead 1. That would be plus 5, and here's plus 10. So plus 8 is roughly in the middle. I'm going to make a dot on my plus 8 for lead 1. And then I'm going to draw a perpendicular line going up through this large circle, like that. Next, lead 3. Well, lead 3 was a negative 2. Need to be mindful that you have it mapped appropriately. Lead 3 is a negative 2, so roughly right there. And I am going to draw a perpendicular line like this, going through. And then there's going to be a point where they intersect. Now you take your ruler, put your pen in the very center circle here, And the idea is you're going to draw a line from the center circle through your connecting dot for the 2 leads and straight out of the circle. So this person has an MEA of 10 degrees. Make sure you remember that the normal values for a mean electrical axis is 10 degrees. Now, I'm going to demonstrate another phenomenon where we were trying to show you a movement of the MEA. Remember in lab, you held your breath. And when you held your breath, you take a deep breath in, and when you do that, your diaphragm contracts and it moves inferiorly. When it moves inferiorly, your heart takes on a more vertical position in your chest. Instead of being slightly tilted up to the left, it hangs more vertically, which means it moves a little bit to the right. When you exhale, the diaphragm is allowed to relax. It domes up, and then you have your heart being pushed on, and the apex gets pushed up more towards the left. So when you do the MEA for the breath in versus breath out, you're going to see for the breath in that the person's MEA compared to rest should shift to the right. And if they are exhaling compared to their MEA, it should be, for regular breathing, it should shift to the left. So let me demonstrate that for you. Let's say, a new example, let's say you do the measurements for lead 1 and lead 3, and let's say for this new example, you calculated an MEA of about 50. Let me just draw all this in. Okay. So let's say your person, your partner, when they were at rest, let's say they got an MEA of plus 50-ish, roughly, at rest. Then you calculate again their MEA for holding their breath in. Again, when they hold their breath in, the diaphragm moves inferiorly and the apex of the heart is now more vertical. Compared to the previous example that I just did, a new one, where the person's MEA was about plus 50, when they held their breath in, there was just a very slight movement of the MEA, in this case, calculated to about plus 62 degrees. Then you map again the person's MEA when they exhale. When they exhale, the diaphragm is allowed to relax and it domes up. And at this point, the diaphragm pushes on the apex and makes the apex of the heart move a little bit more towards the left. So you'll notice that the person's MEA went from a plus 50 here to about a plus 42. It went more towards the left, and that's what we would expect to see. If you calculate that your partner's MEA did not move to the right or left appropriately, if it didn't move right when they took a deep inhale, if it didn't move left when they took a deep exhale, then they probably were not trying their hardest to change the position of their heart, because I didn't tell you all that that was in fact what you were trying to do. But that should have been the outcome. And I do test you on what should have been the outcome. Most of you will get a similar result.